Let's take a look at our lesson objectives for this review lesson. First, we'll practice determining if a reaction is at equilibrium. Then we'll introduce an analogy for chemical equilibrium. And lastly, we'll practice using the Chatelier's principle. We're going to start with a brief discussion of a German scientist named Fritz Haber. And during World War I, he developed new chemistry to allow the Germans to make explosives. This process was called the Bosch-Haber process because it was co-developed with another scientist with the last name of Bosch. It combines nitrogen and hydrogen into NH3. The NH3 is called ammonia, and ammonia can be used to make explosives. But it also has a peaceful use. It can make fertilizer, and that fertilizer allows modern crops, so ammonia can be used to make fertilizer. Fertilizer can have negative environmental consequences, but the world would starve without the Bosch-Haber process. So Fritz Haber has a very mixed legacy. On the one hand, he developed explosives. On the other hand, his process feeds billions of people. We'll come back to our friend Fritz Haber at the end of the lesson. Now let's consider, is a reaction at equilibrium? And the reaction we'll consider is the Bosch-Haber process. This question says, a reaction vessel making ammonia contains 0.67 molar N2, 1.95 molar H2, and 22 molar NH3. Is the reaction vessel at equilibrium? If not, which direction will it run to reach equilibrium? Okay, well, let's go through the steps here. First, we want to write the reaction quotient for the reaction. Remember, that kind of monitors our reaction progress. Then we'll calculate Q and we'll compare it to K. Here's where we're going to develop an analogy that will hopefully help us understand chemical equilibrium. We're going to consider if a reaction were the 100-yard dash. So here we have a racetrack, and let's say this is our starting line. If this is our starting line of a chemical reaction, that means we're going to have no products, because think about it, we haven't started the reaction at all. And that means it's all reactants. If we think about what the Q would be there, Q at the very beginning of a reaction, if there's no products, will be 0. And then we're going to run down the track, and let's say we get to halfway. Here we'll say Q is 50, basically just marking how many yards we've marched down that racetrack. And then at the very end, the finish line, Q would be 100 because it's a 100-yard dash. So Q has tracked our progress through this race, but notice there's something very special about that finish line. It's the exact point at which we're done, which we would call equilibrium. That's where Q is equal to K. Okay, with that analogy in place, let's jump back to our question. Here we've said in step 2 that we would calculate Q and compare it to K. And what we're doing there is trying to figure out if we're before the finish line or after the finish line. So if Q is less than K, we would be in this situation. K we know is 100, and let's say Q is at 50. Blue represents where we're at in the race, and we're not done yet. So that means the reaction would have to run forward. So if Q ends up being less than K, the reaction must run forward. If Q equals K, well, remember, K is equal to 100. That's our finish line. And if Q is also in 100, then we're at the finish line. That means we're at equilibrium. So if Q equals K, the reaction is at equilibrium. What about if Q is greater than K? Well, K is 100, and then that would be like Q being 105. That means we've run past the finish line. We've gone too far. We'd have to run backwards. And so if Q is greater than K, the reaction must run backwards. Well, let's actually calculate Q. So step 1, we need to write the reaction quotient. Remember, products go on top. That's NH3. And we're going to have to square the NH3 because of the 2 in front of NH3. On the bottom, we'll put reactants. We have N2. That will be raised to just the first power because there's a 1 in front of N2 in the chemical reaction. What would be the last part of this reaction quotient? That's right, it would be hydrogen, and we'd have to cube it. Okay, well, now we can actually calculate Q and compare it to K. So we'll plug in our concentration of NH3, that's 22, and we'll have to square that. And remember, that's just given in our problem. Then we'll divide that by 0.67 raised to the first, that's the concentration of nitrogen. And we'll divide by 1.95, the concentration of hydrogen, cubed. When we calculate that, we'll get 97.42. Okay, well, keep in mind that for this reaction, K is 688. And so what we want to do is we want to compare Q and K. In this case, Q is less than K. Our finish line is no longer at 100, This apparently is a 688-yard dash, a much less pleasant race, and Q is all the way back at 97.4. So that, of course, means we're not at equilibrium and that the reaction runs forward. Okay, with this all in mind, let's now jump into Le Chatelier's principle. And I think Le Chatelier's principle will make a fair bit more sense with this analogy in place. Let's say that a reaction vessel making ammonia is at equilibrium. What will happen if more reactants are added? Here's the key. For all of our Le Chatelier's problems, they start at equilibrium. So in this case, if our equilibrium constant is 688, then our Q is also 688. We're at the finish line of the chemical reaction. And here's the thing. Remember that Q can be written as NH3 over N2 times H2, but that's telling us that we have products over reactants. So if we add reactants, we're increasing the denominator. That's going to pull us back from the finish line. It's like we're adding more of that starting stuff, so we're not done. So when we add reactants, we're going to pull our Q backwards. And that means the reaction must run forward again. So what will happen if we add more reactants? The reaction must run forward. That means if we added either of the reactants, it would make more NH3. Okay, well now let's consider what would happen if more products are added. More products means that we're adding more of the finishing stuff. So adding products is going to increase Q. That means we're going to be past the finish line. And to get back to equilibrium, the reaction must run backwards. So ultimately, if more products are added, the reaction must run backwards and we'll make more nitrogen in H2 to get back to equilibrium. Let's look at another example. A reaction vessel making ammonia is at equilibrium. What will happen if products are removed? So this time we're removing products, and that means Q is going to drop. So if Q drops, we're pulling back away from the finish line, and to get back to equilibrium, the reaction must run forward again. So ultimately, if products are removed, the reaction must run forward again. All right, what about if reactants are removed? Well, remember, reactants are like that starting stuff, and I have just the right amount of them when I'm at equilibrium. If I take them away, I'm going to have too much of the finished product and not enough of the starting stuff. That pushes me past the finish line, and so the reaction's going to have to run backwards to get to equilibrium. Okay, let's look at another type of change. This one says a reaction vessel making ammonia is at equilibrium. What will happen if the pressure is increased? So here's the deal. Higher pressure favors the side with fewer gas moles. And so when we look at our Bosch-Haber process, we see that there's 2 moles of gas on the product side and 4 moles of gas on the reactant side. I get 4 when I add the 1 to the 3. And that means that if I increase the pressure, it's going to go to the smaller side, and that means products are favored. If we think about this from our racetrack analogy, it's a little different though. K is 688, and we're at equilibrium, so our Q is 688. If we change the pressure though, we actually move the finish line. So changing the pressure moves the finish line. And the runners must run forward again. So ultimately, what will happen if pressure is increased? The products will be favored. Now remember, this chemical reaction is used to make fertilizer, and it was developed by Fritz Haber. He knew he wanted to make products. He knew he wanted more ammonia. So do you think he ran it at high pressure or low pressure? Fritz Haber ran his process at high pressure so more products would be made because he knew Le Chatelier's principle. Let's review what we've learned. First, we practiced determining if a reaction is at equilibrium. We talked about how you must calculate Q, the reaction quotient, and compare that to K, which is like the finish line of our chemical reaction. Then we introduced an analogy for chemical equilibrium. We said equilibrium was like the finish line, and Q is like where we're actually standing in the race. Lastly, we practiced using Le Chatelier's principle with this race analogy. Hey, hey.